Some examples of verifying some more trigonometric identities. We've already looked at the process of verifying and what it means to verify, and we came up with a plan to verify. This video is all about looking at some examples. Our first example is sine squared of t divided by tan squared of t equals cosine squared of t. I might begin this by looking at the left side of my equation because it's more complicated. And something that's more complex, we can usually simplify by combining different trig identities. It's often a little bit more difficult to expand something simple into a more complex form. Okay, I'm dealing with sine, cosine, and tangent here. I recognize that tangent is comprised of sine and cosine, so it might be a good idea to turn this tangent into a sine and cosine term. And if I do that, I've got sine squared of t divided by, tangent is sine over cosine, so tangent squared is sine squared t divided by cosine squared t. And I'm just going to bring down my cosine squared t on the right side. Let's rewrite this as a multiplication problem. If I'm dividing fractions, I need to flip the second thing and then I multiply. So I'll have sine squared t times cosine squared t divided by sine squared t equals cosine squared t. When I multiply these guys out, I can pretty quickly see that my sine squared t on the numerator of the first fraction and my sine squared t on the denominator of my second fraction are going to cancel to 1, which leaves me with 1 times cosine squared t, or cosine squared t equals cosine squared t. What we've done is taken the left side of the equation, made it look just like the right side of the equation, which allows us to verify the identity. It's important for us to know that we didn't change the right side at all throughout this process. That's a really good goal to have, so that we can maintain our same goal where we're attempting to transform this to, and so that we don't have to worry about making any math mistakes on the right side. Our second example is going to involve a little bit of factoring. And what I'd like us to remember is when we were first dealing with some of the harder quadratic style factoring problems, we could replace a variable with something else. So I might take a look at something like, okay, I can see that there's a secant to the fourth power, a secant squared, a tangent to the fourth power here. What if I made secant squared of x equal to, and let's use z kind of arbitrarily. Well, secant to the fourth is secant squared squared, so this would be z squared minus 2, that's my z, plus 1 equals tangent to the fourth of x. We can see pretty quickly that z squared minus 2z plus 1 is the same thing as saying z minus 1 quantity squared, which equals tangent to the fourth of x. Okay, let's plug my z back in, and I've got secant squared of x minus 1 squared equals tangent to the fourth of x. We have a Pythagorean identity for secant squared of x minus 1, which is just the tangent squared of x. So we have tangent squared of x squared equals tangent to the fourth of x. If we just square the left side term, we arrive at our verification. Here the key was being able to factor the trigonometric expression as a quadratic. It takes a while to begin to be able to see these trigonometric expressions as quadratic expressions, but we can simplify that by substituting another variable for the whole thing and adding this back in at a later point. Okay, in our next example, we have an addition on the left side and a multiplication on the right side. We have tan x plus cotangent of x equals secant of x times cosecant of x. It doesn't immediately look like we can combine everything. So let's see what happens if we turn the left side into sine and cosine. Sometimes that allows us to simplify things a little bit more. So this is about converting to sine and cosine. So tangent of x equals sine of x divided by cosine of x. Cotangent of x equals cosine of x divided by sine of x. And once again, we're going to leave the other side completely the same. To be able to add those two fractions together, I need to make use of some common denominators. I'm going to multiply the sine x over cosine x by sine x over sine x, and cosine x over sine x by cosine x over cosine x. The left fraction turns into sine squared of x divided by sine x cosine x. The fraction on the right turns into cosine squared of x divided by sine x cosine x. And as always, we're left with exactly what we started with on the other side. When I add these things together, I get sine squared of x plus cosine squared of x, hopefully that's setting off some alarms, over sine x cosine x, leaving my secant x cosecant of x alone. Sine squared x plus cosine squared x is our initial Pythagorean identity, which equals 1. So the top goes to 1, the bottom remains sine x times cosine x. What I'd like you to see is that this is the same thing as saying 1 over sine x times 1 over cosine of x. And we know something about the reciprocals of sine and cosine. They're equivalent to saying cosecant of x and secant of x, respectively. From there, it's just a matter of using the commutative property of multiplication to transform the final equation and verifying the identity, showing that the initial identity is true. In our next example, we're dealing with another problem where we have a sum and another operation, in this case a quotient. I'm really good with cosine squareds and sine squareds, but not so good with things that are just to 1 power. The left side also has things written as 1 fraction, which can be kind of useful. while the right side of the problem does not. I also like that the left side is written in terms of cosine and sine. Maybe if I convert the right side to cosine and sine, that will help us out. So in this case, I'm going to leave my cosine theta over 1 minus sine theta and work with my right side, secant theta plus tangent of theta. If I begin by writing these as cosine and sine, I'm going to have 1 over cosine of theta plus sine theta over cosine of theta. That's actually rather convenient because they have a common denominator. And that can make for a little bit of easy adding, which is 1 plus sine theta over cosine theta. Here's where a little intuition needs to come in. I can see that these two fractions look pretty similar. I have cosine theta over 1 minus sine theta, and I have 1 plus sine theta over cosine theta. It would be really nice if I could find a way to get this to 1 minus sine theta, or maybe even to get rid of the cosine. So what I'm going to try to do is rewrite this fraction by multiplying by 1. And the one I'm going to choose to multiply is going to be 1 minus sine theta over 1 minus sine theta. The reason that I'm choosing to do that is that I see the denominator on the left side is 1 minus sine theta. And also I see a difference of two squares things happening on the numerator of the right side fraction, which is going to leave me with 1 minus sine squared of theta over cosine theta times 1 minus sine theta. We know from our Pythagorean identities that 1 minus sine theta is the same thing as 1 minus sine squared theta is the same thing as cosine squared of theta. If I keep the denominators the same, we can cancel out one of my cosines to 1, leaving me with cosine theta over 1 minus sine theta. If I bring down the left side of the problem, cosine theta over 1 minus sine theta, we can show that we have verified this identity.